Very much. Welcome to our monthly webinar series. We're dealing with small systems, and today's topic is corrosion control for drinking water systems. So welcome very much. And a couple of housekeeping duties right up front. One is we're offering continuing education contact hours, and if you haven't requested credit for those, you can still request them at the website below here on this screen. It's also provided on the screen under number 3.2. To receive the contact hour, you must be registered or be in a room with somebody who's registered. You must attend for a minimum of 60 minutes. And if you're in a room with others, the people who are not logged in, those people's names need to be provided by the person who is logged in. And the email address is right there that you can send that information to. The certificate, this webinar will be on a website, but we cannot offer certificates of completion for listening to the recording of the webinar, only the live webinar itself. So with that, we can move on. And we're going to be using, before I introduce our speakers, we're going to be using the questions box for a couple things. One is if you've missed the poll question of how many people are in the room, it was put on about 5 minutes ago. If you've missed that, if you've got more than one person in your room, please use the question box on the right drop-down dialog box, and let us know how many people are in your room if it's greater than one. That would be great, because then we can quantify how many people this webinar is reaching and justify its importance. And the second thing we will do with the questions box is if you have a question for the speakers, even during the speakers' talk, please put it in the question box. We'll sort it out and we'll answer them at the end of both speakers. So we'll be answering questions at about 50 minutes into the presentation after both speakers have talked. Now, with that, our first speaker is Brian D'Amico. Brian is a chemical engineer who's spent the last 10 years at EPA working on water regulations, both through the Safe Drinking Water Act and the Clean Water Act. He is currently the team lead for the regulations implementing Section 1417 of the Safe Drinking Water Act. Prior to this transition to drinking water, Brian worked on several effluent guidelines, including airport de-icing and unconventional oil and gas. So with that, I would like to pass the webinar over to Brian for his presentation.
Thanks for that. This is Brian. So today we're going to go over the current lead and copper rule and some of the requirements for the background on the existing lead and copper rule, and specifically some of the optimized corrosion control provisions. So I think, as we all know, the lead and copper rule is a treatment technique rule. It requires systems to take certain actions to minimize lead and copper in drinking water, as opposed to a traditional national primary drinking water regulation where you'd meet an MCL. It requires public water systems to monitor for lead and copper, and again, no MCLs, but there are action limits of 0.015 mgls for lead and 1.3 mgls for copper. If the action level is exceeded, it triggers additional actions designed to reduce water corrosivity, provide public education, or potentially removing lead service lines if necessary. Both community water systems and non-transient non-community water systems are subject to monitoring requirements for lead and copper. Systems must collect first draw samples at taps in homes or buildings that are at high risk of lead and copper contamination. 40 CFR 141.86 outlines some of the considerations when selecting the homes or buildings that you sample. The number of samples that are required to be taken varies by the population served by the system. Systems serving over 100,000 people have to take 100 samples, down to systems as small as less than 100 people only need to take 5 samples. Public water systems must conduct tap monitoring every 6 months unless they qualify for reduced monitoring. the number of required samples and frequency may be reduced if the systems meet certain requirements. For example, a system serving less than 50,000 people that is below both action levels for 2 consecutive 6-month periods, they can be reduced to annual sampling. And the monitoring may be as infrequent as once every 9 years. In the event a public water system exceeds the designated action level, they may be required to take corrective actions to minimize the levels of lead and copper in the water. Some of these may be required regardless of lead and copper levels, particularly for large systems serving more than 50,000 people. When a public water system exceeds an action level, they must conduct the following corrective actions. They have to conduct public education. This could be something as simple as putting, a flyer in your utility bill. They have to implement source water monitoring and, if needed, treatment. Install or optimize previously installed corrosion control treatment, particularly for those serving less than 50,000 people, or implementing lead service line replacement if necessary. Lead service line replacement is only required when corrosion control does not reduce the lead and copper levels below the action level. So if you have your optimized corrosion controls in place and it does not reduce your lead and copper below your lead below the action levels, then you have to get to lead service line removals. And again, some of the corrective actions are required of large PWSs, those over 50,000 served, regardless of the status of their action level monitoring. So what is corrosion? IUPAC defines it as an irreversible interfacial reaction of a material with its environment which results in the consumption of material or its dissolution of the material into the component of the environment, which basically means there's a chemical reaction within the water that degrades the lead, and it carries the lead away essentially into the drinking water system. So why do systems want to control the lead, or want to control corrosion? And that's because, as we said, corrosion can cause the dissolution of lead or copper into pipes, into drinking water. And there are 3 specific approaches laid out in the lead and copper rule. One is pH or alkalinity adjustment. One is a corrosion inhibitor addition, such as orthophosphate or silica. And one is calcium carbonate precipitation. So looking at those three scenarios, increasing the pH of water may decrease the solubility of lead and copper in water. Sodium carbonate, lime, sodium hydroxide, those are 3 agents that you can use to increase the pH of drinking water. That being said, if you do have higher pH in your drinking water, it may cause disinfection byproducts such as chloroform when chlorine-based disinfectants are used in the drinking water treatment plant. Additionally, you could inject orthophosphates into your drinking water. It creates a coating on the inside of the distribution system. The coating hinders the ability of the lead to dissolve into the drinking water. You would like to have your pH of your drinking water in a range of 7.2 to 7.8 to ensure that the orthophosphate is evenly distributed throughout your system. And unfortunately, orthophosphate may result in increased nutrient discharge to receiving waters. The last option specified in the LCR itself is precipitating calcium carbonate in the water distribution system. The precipitation may be achieved by adding lime to your drinking water. And calcium carbonate will then form a protective scale on the distribution system, once again limiting the amount of corrosivity to that lead because it has that scale on it. It's not the preferred method. It's difficult to precipitate an even scale throughout the system. You tend to have a much heavier scale closer to the treatment plant and little to no scale towards the end. Most large public water systems and medium and smalls that exceed the lead or copper action levels are required to optimize their corrosion control treatment. All large PWSs and some small and mediums are also required to conduct a study of their system to determine the best TCT to install. The study has to be completed within 18 months, and once it's been approved by the state, the system then has 24 months additionally to install that technology. Once it's been installed, they must conduct follow-up monitoring for 2 consecutive 6-month periods. Includes both tap and entry point monitoring. And you're going to be looking for not only lead and copper, but also any state-designated water quality parameters, pH, alkalinity, conductivity, whatever the state deems appropriate. And after follow-up monitoring has been completed, the state reviews the data and sets the optimal water quality parameters. And that defines what the optimal CCT is. Compliance is determined by meeting those optimal water quality parameters. Monitoring continues at the tap every 6 months and at the entry point every 2 weeks. And if you consistently meet your parameters, you can reduce the frequency at which the tap monitoring is required. And once again, as we discussed prior, the monitoring can be as frequent as once every 9 years through continued compliance. And that's all I have, although it sounds like we hold questions till the end. So I will now turn it back over.
With people. So thank you very much, Brian. Our second speaker will be Michael Schock. A little bit more housekeeping. Again, if you missed the poll in the beginning, if you have more than one person in your room, please go to the question box on the right dialogue drop-down menu and indicate how many people are in your room. That would be great and very helpful to us. Also, if you have a question during the talks, feel free to put that into the question box, and that's what we'll be using as our list of questions to answer once Mike Schock's done. With that, to introduce Michael Schock is a chemist with ORD's National Risk Management Research Laboratory in Cincinnati, Ohio, where he has spent the last 30 years of his career conducting drinking water research with an emphasis on metal release mechanisms and predictive modeling, corrosion control, pipe scale and sediment and inorganic water analysis, contaminant accumulation, and water quality in domestic plumbing and municipal distribution systems. He has received numerous awards, been on numerous advisory committees, and has had dozens of publications. And one of his awards was the 2011 AP Black Award for Lifetime Achievement. So with that, Michael, I'd like to pass the webinar to you.
All right, thanks, Tom. What I'm going to talk to you about the treatment, control, and assessment strategies for lead and copper release into drinking water. And the reason why I call it metal release is when we talk about optimizing corrosion control treatment, we're really talking about reducing the release of the metals into the water. And those are several different mechanisms. It includes both the pure corrosion and control of metal release, but it's more than simply adjusting pH or adding phosphate. The nature of the pipe scales that are out there in these distribution systems reflect the past treatment history, and they dictate kind of the level of direction and the level of success of the different control strategies. Metal solubility is still important because if you look across systems, it varies by a factor of 5 to 10 or more, and it's the minimum chronic background exposure the consumers get. So it's important both to control soluble and particulate lead release, particularly. And you can definitely control lead release very well. Soluble lead release is more difficult to control. Particulate release and episodic lead spikes can't be totally prevented when the sources of lead remain present, even though they can be reduced in frequency. So corrosion control treatment, we usually use the term, it's really intertwined with all treatments that affect the distribution system water chemistry, because to achieve the optimal treatment overall, you need process control and distribution system water quality optimizations as well. So it's not an independent, separate process. And as long as lead pipes are there, and there are millions of lead pipes out there, they're not going to go away anytime soon. They're not like faucets that wear out or old galvanized pipe in a house and needs to be replaced every 30 or 40 years. Shown here is a photograph of a lead pipe installed in Cincinnati just after the Civil War. It's been 150 years, and you can see that it's been hardly touched by any action and interaction with the water. So these pipes are going to be there for another century or more unless they're taken out for some other reason. The other reason why we're concerned about lead particulates is if you look at the percent lead by weight in different scales. For instance, the protective films that we try to make to reduce lead solubilities are composed mostly of lead. And the standards that require remediation for lead paint and lead soils are infinitesimally small compared to the routine levels of lead you find in these particulates that make up the scale. So even if you have a perfectly treated system with orthophosphate, you've got 75% lead in any little particle that flakes off of that coating. And with the carbonate scales or the lead fluoroxide scales, you're looking at 80% or more lead. So controlling the particulates is very critical as well. Now, what governs the lead levels that you observe? It's partly a function of the sampling protocol, where you're looking what the lead release, what the contact of the water is relative to lead sources. The solubility of the lead surface material is important, and the rate of dissolution, because you're looking at relatively short stagnation times. They're not really at chemical equilibrium. So things like the galvanic driving force or the rate of diffusion from the surface are critical. The length of contact with the lead surface and the nature of the lead release. Is it particulate with these high percentage but small particles, or soluble lead? And there's a temptation to try to use surrogate monitoring techniques to predict lead levels, what's really happening at the tap, or the idea of corrosion indices, but actually there are no pipe rigs or water quality parameters that can predict the lead levels at the tap. The only way you can really find out what's happening, the net result of all these chemical reactions, is to actually measure it. Now, there are a couple misconceptions in the lead and copper rule. I think people have tended to misinterpret things. One of them is the idea that the water quality parameters are predictive and that by themselves they can control the lead levels. The real reasons why they got in there is there were instances of systems turning the water treatment on and off, on right before the monitoring, off after the monitoring. They're there to try to make sure the corrosion control that was successful is kept in place, keeping the pH adjustment, keeping the inhibitors in there, and keep systems from just willy-nilly changing water sources and causing problems. So there was an intention of these parameters to try to really get more consistent water quality. And there's also kind of a misconception that because it's a treatment technique rule, the health effects are less serious than in regulations that have MCL. But actually the lead rule was a treatment technique rule because of unknowns about the feasibility and what levels of lead control could probably be achieved. The MCL goal is still 0. And the risk estimations, current research based on IQ detriments, blood lead level elevations, and other cognitive disabilities still point to a necessity to achieve lead levels of even less than 5 parts per billion, at which measurable health effects are still being seen. So it needs to be taken just as seriously, even though it isn't an MCL. Really, the ultimate solution is to fully remove the lead pipes. There are certainly logistical and legal barriers to it, but research that we've collaborated on, particularly with Madison, Wisconsin, where there are a lot of measurements were done, showed that even though the lead levels didn't reduce immediately from the full replacement of the lead pipes, that the lead levels did go down substantially and dramatically, but it took about 4 years for that to happen. And the reason why was because of accumulated manganese and other sediments that were in the premise plumbing that accumulated lead and were still there after you took out the pipes. So taking out the pipes was still important long term. It just didn't have an absolute immediate effect. And a couple other systems in Guelph, Ontario, and Halifax, Nova Scotia, they did similar kinds of studies looking at the impact of what full lead service line replacement, and without these manganese and iron-rich coatings inside the pipes, they achieved immediate and permanent reductions in lead. So it's important when it can be achieved, and for systems without many lead pipes, this is probably the most cost-effective measure that can be done. Now, when you look at lead pipe scales, there are many kinds of pipe scales on the lead pipes. They can be the simple carbonates and hydroxides, simple lead 2 orthophosphate minerals, and simple lead 4 oxides is all described and were assumptions under the development of the rule. But there can also be mixtures of lead 2 phases. And there can also be diffusion barriers, materials that aren't really lead corrosion byproducts, but that they can prevent the release and migration of lead into the water. They can be insoluble or amorphous lead phases, but they can be adherent non-lead phases. And there can also be surface following deposits, and these are really difficult to deal with because they cause a lot of lead release problems. for utilities. These are primarily not made of lead. They're usually not crystalline either. Lead can sorbed to their surface, and they often don't adhere well, and so they come off with lead as particulates. Now, Brian mentioned one of the original classical techniques for control is using pH and alkalinity adjustment to make insoluble lead minerals on the surface of pipes. If you have lead pipes, it's quite difficult because the only way you can get pretty low solubility is if pH is in excess of 9, in the 9 to 10 to 10.5 range. And even if you achieve that, it's likely never as good in terms of soluble lead as lead 4 oxide or even the orthophosphate treatments. And the carbonate solubility is also important because when you change background water chemistries, the fastest reactions are the carbonate reactions. So even though if you're adding phosphate and you're trying to re-equilibrate new conditions, what happens in the initial disturbance will affect the carbonate minerals. And so if you're trying to drop your pH from a high pH adjustment system to 7.5 to do orthophosphate treatment, the lead levels are going to go up dramatically for quite a period of time while you're doing the transition. Now, one of the concepts that's been around for a long time but is just receiving more recent attention is the concept of point of diminishing returns as the key to cost-effective orthophosphate dosing. And this is really the way to approach orthophosphate treatment. It often hasn't been done this way. Usually systems have added just enough phosphate to squeak under the action level. But if your intent is really to minimize the lead release, minimize the lead exposure, you need to look at what is the amount of phosphate you add until you reach this point of diminishing returns where increments of phosphate additions stop giving you real benefits in terms of lead release. Theoretically, and this we've shown for a long time, it's dependent on the pH and it's dependent on the carbonate level in the water. For instance, at a low carbonate system, about 5 milligrams per liter is carbonate. You can see the point of diminishing returns happen between about 1 and 2 milligrams per liter is PO4. But at a higher carbonate level, you really don't start seeing a distinct point of diminishing returns until 3 or 4 milligrams per liter is orthophosphate. And once again, the pH, there's more pH dependency at the high carbonate level than at the lower carbonate level. Just as a matter of note, in the United Kingdom, where phosphate dosing is basically the universal approach, their average doses are typically 4 to 6 milligrams per liter as PO4. This illustrates the idea of point of diminishing returns and the effectiveness of higher dosages of orthophosphate. You can see that elapsed days after the addition of phosphate in some studies in the early 90s that higher phosphate dosages more quickly achieve the lower lead levels, and you actually do achieve lower lead levels at a point. Now, one of the ways we can evaluate the successfulness of the phosphate treatment, both to dissolved and particulate, is looking at the aggregated data in the UK. And they approached their optimization program starting in the middle 1990s by doing first an initial dose estimation by pipe rig studies in the background water, and then doing random daytime tap monitoring to assess both the progress of the corrosion control and the exposure. And the nice thing about this kind of sampling program is while you take lots and lots of samples, they're not as invasive, and they do give you a more direct relationship to the exposure that people have under normal water use, and it also is a very good direct comparison of the effectiveness of the treatment on both dissolved and particulate lead because it doesn't differentiate. And what you can see is as the phosphate levels go up and as time goes on, much, much lower lead levels were achieved. This figure, there's a breakdown where they looked at properties that had lead pipes and properties that did not have lead, or properties that included all properties, many of which didn't have lead. And you can see that the trends hold up the same for both, but the leaded properties see an especially dramatic decrease between 1995 when they started their optimization and 2005 where they began to get relatively stable conditions. And the lead release was improved both for systems that had lead pipes and also for the properties that had other lead sources such as brass or soldered joints. And some research we've done here at EPA is we've looked at the efficacy of phosphate at higher pHs because we know that the optimal pH for lead-2 solubility with phosphate is in the mid-7s kind of pH. But we wanted to see are the predictions, the calculations and theoretical predictions of also some efficacy at high pH, do these hold up? So this is a set of experiments at a DIC of 10 and 1 milligram per liter of phosphate. And we see that even as the pH got up into the 8.5 and 9, there was still a benefit relative to the non-phosphate treatment. So here we can see, we saw for the first time an indication that, especially at a pH of 9, systems that have very high pHs may in fact be able to get better performance just supplementing orthophosphate and not having to go through a radical depression in pH of 2+ units. Further experiments that were just done a couple years ago by Stephanie Miller, a graduate intern here. We looked at a much higher pH and looked at different phosphate dosages, pH of 9 and DIC of 6, which represents many waters, and especially in the northeastern part of the country. We could see that at 1 part per million of orthophosphate achieved much, much lower lead levels than no phosphate at all. We didn't get the same trend of decreasing lead as phosphate was increased that we saw at lower pH, but we did see a distinct benefit on new clean surfaces with the addition of phosphate. Now looking at lead-4 scales, lead-4 is commonly occurring, although only a small number of systems have complete lead-4 coverage of their pipe scales. About a third of the pipe samples that we've looked at have at least some lead-4 material. These scales are nice when they're adherent, when there aren't problems with physical disturbances, because you can achieve very low lead levels, sub 10 microgram per liter kind of levels in contact with lead pipes. And this is an example of some profiles that were done in locations in Cincinnati. You can see even after 10 hours of stagnation, we're only seeing less than 5 parts per billion lead in contact with the service line. Now, when you have lead-4 scales, the two most important parameters to control in the system are really the disinfectant demand, so that you can maintain a high oxidation reduction potential, which indirectly relates to the amount of free chlorine that's added to the water. But you want to minimize your disinfectant demand so that you don't have to over-add the amount of chlorine to keep the ORP high. But these scales can be destabilized two ways. One is if you let the pH drop in the system, you can get into lead-2 solubility, and lead-2 solubility is far higher than lead-4 solubility. And the other way is if you lost free chlorine, and the ORP dropped, then you can redissolve these scales and turn them into lead-2 carbonates, and those are much more soluble. Now, some people get confused when you add more disinfectant. They think that it's increasing corrosion, but lead and copper rule samples tend to be taken in the 6 to 16-hour range, but more likely closer to 6 hours, because that's the practical standing time overnight or during the day for consumers. So you're not really in equilibrium condition, so there's still a chance the lead levels would normally go up over time before they plateau out. Also, adding more disinfectant may just speed up the rate at which it's released. So in a given time period, the lead's going up quickly. It appears to be higher, but if you let it go for 16 or 20 hours, the lead level would stop incrementing. So there is this interaction to keep in mind. It gives the illusion of more corrosivity, even though it isn't. Now, something that we've really discovered in the last 20 years is taking on huge importance is the significance of non-lead scale components. And these actually may be more prevalent than the normal lead solids when you look at all systems. This slide shows an example of these kind of materials. They're rich in manganese, iron, aluminum, calcium, or silica, depending on the system. And adding orthophosphate or trying to adjust the pH when these coatings are on the pipe really won't minimize lead release until the causes of these interfering buildups are controlled. This is an example of some profiles that were taken from a water system that has a surface deposit that's actually got less than 10% lead in it. There are no lead crystalline lead phases, but it's very rich in aluminum, silicon, and calcium. And you can see that there are pretty high lead levels in contact with the service lines and even the premise plumbing in this kind of scale. So it's not sufficiently protective, even though it doesn't have very much lead in it. There's an analysis. We did some research in Chicago where they use a blended phosphate. This is a mix of ortho and polyphosphate. For a long time, it was thought that these work by forming crystalline lead to orthophosphate compounds, that the orthophosphate component is really doing the protection. But what we found in these scales in the system was actually there isn't very much lead in these scales, that they're very high in aluminum and calcium and phosphorus, and it certainly serves as a diffusion barrier, but it's not immobilizing by the mechanism that was originally thought. So there are a lot of impacts of these dissimilar coatings. They can sorb or entrain lead or copper. Even after lead pipes are removed, they can continue exposure. They degrade the performance of the phosphate inhibitors. They're prone to releasing particulates. So you have to understand the treatment change impact on the coatings as well as just on lead or copper corrosion per se. And one of the other problems we're discovering is you can't really predict the optimization or effectiveness of phosphate addition from theory on these kind of mixed non-crystalline solids. But you can pilot test them, and that's the basis by which a utility can ascertain the best conditions to stabilize and reduce the lead release. These dissimilar coatings interfere with the lead-4 formation, so that's not really an effective option. And to control the lead release in these systems, you really have to control other factors. The iron corrosion and deposition from upstream mains, the finished water manganese concentrations, removal of DBP precursors, for instance, instead of switching to chloramines, coagulant carryover, and things like that. A system that in Wisconsin, a good example of this is some work Abigail Cantor did in Marshfield, where the system had wells that had a lot of manganese in them, and so they went out and they flushed the lines and they tried to remove as much particulate manganese as they could, and they actually achieved complying with the lead and copper rule action level purely by just cleaning out the manganese deposits and not introducing any other kind of corrosion control treatment. Then in 2010, there wasn't as much unidirectional flushing, there wasn't as much main cleaning, and while they still managed to meet the action level, the number of hits on higher lead concentration sites went up considerably. So this was really good evidence that the particulate material and deposits in the system were really interfering and causing lead exposure increases. So now moving on a little bit to copper. Even as early as 1992, an AWWA-funded study was showing that there was a very poor correlation between high lead and high copper occurrence in the monitoring sites. And really the only place that they overlapped well were in oxic waters that were somewhat acidic. So some of the issues that we've discovered now, the science issues, the chemistry and mechanisms of lead and copper release are quite different. The newest Tier 1 copper sites are now 25 years old, and they get older every monitoring period. So this is the inverse of the risk of copper release, which is new surfaces. If a site has a lead service line, it's still sampled for copper, and so often the copper, there isn't any because many of the lead service line sites actually have galvanized plumbing in the interior. It's also possible for states to deem systems optimized with copper, even if the copper levels are above the action level, but there's no public notification, so the public doesn't realize that in new construction they can be exposed to high copper levels. And also, water quality varies in many distribution systems with multiple sources, multiple treatment plants, and so where the sampling sites exist may be considerably different than where the high copper levels exist, which would be, for instance, new subdivisions that might have their own water supply. And so the site targeting within systems of varying quality doesn't really capture the aggressive waters. The main factors in copper release, oxidation reduction potential or persistence of oxidants. Not the same way as lead-4, but the difference between copper-1 chemistry and copper-2. Copper-2, the more oxidized form, is far more soluble. pH, alkalinity, and orthophosphate make a huge difference in copper-2 solubility. Huge factor is aging, and this was just something that was discovered in the middle 90s after the development of the lead and copper rule. As copper scales age in the absence of corrosion inhibitors, the copper solubility goes downwards, and it goes downwards by a factor of 50 to 100. So old copper sites will give much lower copper levels. Stagnation time is different. Lead tends to plateau at about 16 hours or so, but copper can go up as long as oxidants persist until it reaches its solubility limit, and this is often 16 to 48 hours or more. And also the surface area to volume ratio of the real pipes matters because that affects the aging process and the on-off operational patterns of the pipes as well. They age faster when there's more on-off kinds of situations. One example here just shows in copper 1, a typical anoxic groundwater, very low solubility, but for instance, if you need to introduce disinfection to a system that's never had it before and you get copper 2 instead of copper 1, you can get even a 1,000-fold increase in copper solubility at pH 7 between copper 1 and copper 2, depending on the carbonate level. The copper 2 is very influenced by pH and alkalinity, but if you have new copper and the DIC is relatively low, even at a pH of 7 or so, you'll never have a problem. But as the alkalinity goes up, you increasingly have copper problems when it's new until it ages. So the copper levels depend on the age, the pH, and the alkalinity. You can see the field highlighted in blue here are the areas that are most vulnerable in new plumbing to having potentially elevated copper levels. Casting it a little different way, looking at it in terms of dissolved inorganic carbon concentration, you can see where the action level is 1.3 milligrams per liter. You can see at low DICs, a little bit of pH adjustment will do just fine. You'll never have a copper problem. At higher DICs, even a lot of pH adjustment won't help, and you'll run into a barrier because of scaling, because of the hardness in the background water before you'll be able to control it by alkalinity control. So the other thing that happens is if you have an issue with copper discharge and wastewater, it's really difficult to get copper levels very, very low without going to very high pHs. There's a couple graphs showing some aging. There have been dozens of papers from 6 or 8 countries that have all observed the same phenomena, showing this huge decrease. On the left, you can see, a nice example in a Midwest water system of how much higher the copper levels are in newer plumbing than the older plumbing. And this is a system that has not made a significant change in treatment or water quality. On the right are a couple systems in California showing water quality affects the rate of aging, even though neither of these systems were exactly over the lead and copper action level. It did show the phenomena and that this is a real serious question that hasn't been looked at very much. Here's another example Midwest system that shows that using lead and copper rule monitoring data that basically they aged themselves out of a problem. After 8 years, by going back to the same sites, or mostly the same sites, the copper was distinctly lower, and finally, and you can see even now, at the end of this data, 11 years after the beginning, you see much, much lower copper levels than at the beginning with no water quality change. And this is just an example of the aging effect. So if you think of the last plumbing age under the lead and copper rule, if it's a tier 1 site, would be in the early 90s, would be the newest possible plumbing. You can see that they're quite old and the chances are pretty small that they're going to have the highest risk copper level. Now if you do have high alkalinity and high carbonate content, basically the two approaches would be to either remove carbonate by some kind of lime softening or split stream membrane filtration or anion exchange or something. The other approach is adding orthophosphate. And orthophosphate will work, but you have to have enough of it. And if you don't add enough of it, you actually make the problem worse by perpetuating the newer surface conditions because the phosphate inhibits the aging. This is some work that a colleague, Darren Lytle, mine did and shows some of the relationships in pilot testing, jar testing for copper solubility. And you can see that the higher copper or the higher phosphate doses can easily get high DIC water, or get copper levels under the action level. And this also holds up for DICs even 50, 60 milligrams per liter. 3 milligrams per liter, 3 to 3.5 milligrams per liter as PO4 will almost immediately get the copper below 1.3 milligrams per liter. These photographs show DIC of 50, which would represent a hard, high alkalinity groundwater. You can see that the phosphate, the top pipes of the pair, inhibit the natural formation, the natural aging of the hydroxycarbonate scale. DIC, just as a reminder, means dissolved inorganic carbon. That's the sum of all of the carbonate species that are in the water. So it would be bicarbonate, carbonate ion, carbonic acid all put together. This is a field study we did at Indian Hill, Ohio, which is a high alkalinity groundwater. DIC in this one is 63 milligrams per liter. That translates, in this water, pH is about 7.3. It translates to an alkalinity of a little bit over around 300 milligrams per liter. And from the time we put in between 3 and 3.3 milligrams per liter orthophosphate, the copper levels dropped. And these were in relatively new plumbing because they didn't have many older Tier 1 sites. It dropped to below 1.3. It dropped to just a little bit over 1 milligram per liter and stayed there consistently. It's kind of remarkably consistently. So this is a successful treatment. Now, phosphate overall, the orthophosphate, as I said, can immediately prevent copper being over the MCLG and the high alkalinities. Blended phosphates, however, have rarely been shown to reduce copper below the MCLG at high alkalinities. But unfortunately, they have been shown to perpetuate copper above the action level. Polyphosphates also have not been successful unless the DIC and pH combination in the background would have worked anyway. Orthophosphates have been shown to be beneficial in terms of copper pitting at both high and low alkalinity, so that's a benefit. And but you must be aware that orthophosphate at low dosages and low DIC can retard or prevent aging, but copper release is not normally an issue from a drinking water standpoint. System that does have a copper problem in wastewater discharge, if they've got very low discharge limits, they may be better off at a low DIC and high pH, just from a copper solubility standpoint. And another thing that's important is with copper, for systems that don't have lead service lines, lead's usually reduced below the action level at lower phosphate dosages than copper. But the extra phosphate never hurts the lead. So lead control shouldn't be considered a constraint, and to not improve the copper levels with higher orthophosphate just because you'd be afraid that the lead might get worse. So to kind of summarize the lead and copper part of the talk, you've got to think in terms of how changes in process could disturb or undermine the corrosion control treatment and metal release. Things like implementing membrane processes post-treatment, softening, anion exchange, or cation exchange softening, for instance, that puts the high alkalinity back in the water could be a problem. Adding polyphosphate for sequestration, anything that makes major changes to pH, calcium, or alkalinity could affect directly or indirectly the lead or copper release. Introducing oxidants to a system that's never had disinfection before could be, or oxidants for iron or manganese removal could push copper into copper 2 and cause a problem. So just be aware of these kind of treatments. You can look at these slides later for specifics, but be aware that there are many things that you don't think of that could indirectly be very important in affecting lead and copper release. And again, there are a lot of water quality factors. Just suffice it to say that many, many things that you wouldn't necessarily think of can seriously impact lead or copper release. So to predict, if you want to predict the changes, you really should go back to sort of the basics. Look for anything that changes pH, DIC, orthophosphate, or ORP. Things that would affect the valence states of these, or the deposition or dissolution of scales. Situations like alum carryover that causes post-deposition that can consume corrosion inhibitors. Optimizing treatment at the plant so phosphate can't react with aluminum or calcium or iron or manganese. Preventing distribution system scaling reactions if you have too much aluminum or calcium. Things along those lines. There are many things to consider. And something to emphasize is, systems need to do pilot studies to look for the target dosages. And especially if you're using things like blended phosphates, or when you have these non-simple lead corrosion or copper corrosion byproduct scales. You need to optimize under the current operating conditions, and you really need to plan the studies because these studies often take years, a year or two to reach equilibrium. So you need to do the studies well in advance of anticipated future changes. And you need to look at anticipate other distribution system metal or radionuclide release side effects. So this is really the same principle as using jar tests for coagulation or column tests for filter media evaluation. There's nothing really different in principle. And I think system-wide optimization is an essential tool for simultaneous compliance. You need to address all of the direct and indirect factors, treat and solve the sources of the conflict rather than Band-Aids, for instance, sequestration of iron and manganese, or just going to chloramines or DVP precursor removal rather than removing the precursors themselves could prevent you from having a metal release episode. Okay, so simultaneous compliance is possible if you recognize the diverse relationships, recognize what distribution and premise plumbing materials you have, because certainly if you've got lead pipes in place, you've got a lot more complications than you do if you have a system that only has lead in brass devices or in lead solder joints. You know, think about addressing the sources of chemical conflict, the holistic and design integration of the processes. Make sure resources are in place to take actions necessary for operations and maintenance of plants in the distribution system, because keeping the distribution system clean, keeping down the deposition and sediments goes a long way in reducing the particulate release, which is the hardest part to control, and the necessity of pilot studies to tailor to the conditions. So now I've gone to a brief section on sampling to identify lead sources. Some of you may have some experience with this, but we've noticed a lot of people have not really thought about ways to diagnose and isolate the lead problems to really guide you on remediating them and finding the right approaches. Now, for the characteristics of lead sources, there are fewer sources of copper. They're generally more uniform. Lead service lines, when present, are the biggest reservoir of lead, so keep that in mind, but it may not be the highest peak value because particulate release could give you higher intermittent peaks. The lead sources within the houses and buildings are numerous hidden locations, a lot of small laterals. They may be located considerable distance from the consumption tap, yet they can contribute to the lead levels. And it's a little sampling instructions details matters. If you tell a consumer or residents to not use water from that specific tap to be sampled, is not the same thing as telling them not to use water from the house or the whole line that feeds that tap, because the first can result in a liter encompassing fresh water, whereas the second one will not. I can skip over this, just a reminder of some of the inconsistency and the spatial non-uniformity of different sources of lead and plumbing in houses and where the contamination can come from. Just a word of caution that people don't think about is the sample volume here. In a 250 milliliter or 1 liter sample, often things like shutoff valves are encompassed in that amount of water. And frequently you can buy NSF ANSI Cert Section 1 certified faucets, but quite often builders and plumbers don't think about that when they put in shutoff valves, and a lot of times shutoff valves are a bigger source of lead than the faucet itself. You can think, one of the things we like to do is think about the volume of water as representing distance in pipes. And this is just a little graphic showing a liter of sample, how much length of pipes of different types and diameters that liter can represent. And the inside diameter, of course, is important in that relationship. This is a diagram where we're looking at an actual layout of a house. You can see where some of the laterals take off from the tap. You can see where the first liter ends. There's a lot of solder joints in a faucet, but later on, much more distance, you can finally get to where the meter is and then ultimately to the lead service line. So you need to think about sort of the volume of the pipe as volume of the sample representing distance. I put in a couple of slides here just to kind of get you started if you want to do this kind of analysis, giving you an idea of some of the different relationships of the volume to the inside diameter and length of pipe. Now, when you're trying to do this kind of diagnostic sample, one of the things to think about is the dispersion. The higher the flow rates will give you a little closer to plug flow, but depending on exactly how many bends are in the system and what the surface characteristics are of the scales, you may deviate substantially from plug flow. So even though that's the ideal case and we aspire to get it, you need to keep in mind that this isn't foolproof, that there are some changes and distortions in the sampling just based on the hydraulics. This is an example of doing sequential sampling, multi-elements at a house. We find that it's very useful to look at copper, zinc, and iron simultaneously with lead because they can often help you diagnose where the lead came from. Whether it was brass, you'll have also zinc and copper currents. If there's an old galvanized pipe, it will co-occur with iron and zinc. When you get to the water main, typically, if it's unlined mains in the system, you'll begin to see increases in iron, and that will help to clue you in that you've now sampled past the service line. So it's a very useful tool. This is an example of a place where they sequentially sampled a place that has some renovation, some work right around a new sink location, and you can see the copper levels go down and down because there was new copper near the sink. But as you got farther away, you got into the old plumbing. But since it went through new copper, it did kind of keep biasing the copper levels high until it got really fresh water. The point I made earlier about the lead and copper rule, the guidance for sampling 6 to 16 hours, copper levels, that can often be very good for lead, reaching near equilibrium conditions, but especially at the 16-hour end. But copper levels can still go up for much, much longer. So there are some constraints, there's limitations no matter how you try to sample, but I wanted to introduce you to this very useful tool that we found. The farther deviation from plug flow, the less accurate in finding the exact locations of the sources. The longer the distance of the tap from the source and the more bends, the more mixing will take place. Samples can be biased by water passing through leaded devices on the way to the bottle. So sometimes you see a high lead spike. It could be a particulate released anywhere along the line, so it's always tempting to try to figure out how many feet ago that particulate came out, but particulates don't flow the same as dissolved lead or copper, so you have to interpret them differently. And also accurately capturing whether or not the system's prone to particulate release under normal use depends on the on-off protocol flow rate and flow turbulence. So one of the things that we found useful is to use wide-mouth bottles where you can take samples at a typical flow rate the consumer would have during normal tap use. So with that, I'd like to acknowledge some of the people who contributed greatly to this talk.
All right, thank you very much, Michael. So now we'll start the questioning of our presenters. On the screen right now, you have the next set of webinars. And just one note before we move on is that the August one has been moved up 1 week to August 18th. Originally on the schedule, it was August 25th. So that's one thing to note in case you have an old schedule. It is up on the web already to register, and registration invites will be sent out later this week. So to start with the questioning, I'd like to ask Brian D'Amico. The first question that's on our question board is if copper concentrations decrease with time, is it recommended you change your sampling sites ever so often to include newer construction?
To some degree, where the sampling occurs is more of a local level concern. I think it's a good idea to mix it up a little bit. Part of the reason you don't want to just, and this actually touches on another question that I think we'll get to in a little bit. One of the reasons you don't want to just ignore older homes that are consistently having low sample results is that things like construction can knock loose scale for lead and copper pipes and cause a spike in the contamination levels in your sample levels. So I don't think it's ever a good idea just to say, these sites we've been sampling have been consistently low, so we're just going to ignore them for now. I think it's we have the mechanism in place to reduce the frequency at which you have to take samples, and part of that is to allow for to allow for the anticipated lower results that will come over time, but while still being mindful that these homes could be a problem, and you're still keeping an eye on them, over the course of time. And I think a lot of newer construction, like new construction, is getting away from copper pipes as a whole. Looking at more plastics. So I think, you really need to look at where you think your potential is for contamination. Just saying, this old house doesn't have any spikes and this is a new build, so we're going to swap out the new for the old. That, I think you need to, it's not as cut and dry, and you really need to look at a bunch of factors. But just because something is old and that you're not seeing contamination in the samples doesn't mean you should just automatically step away and say we're done with this site. You still need to be mindful that prolonged periods of low contamination doesn't mean it can't kick up again.
Okay, thanks, Brian. This is very much related, I think. So is allowing a system to age out a feasible option for OCCP if they then achieve low copper concentration?
Again, the mechanisms are there to reduce frequency, so you're not constantly going back on a 6-month or yearly basis and to see low numbers. But I don't think it's wise to just say we've had a history of compliance, we're just going to forget these entirely, because construction within a home, construction in the system can kick up, scour in the pipes and knock loose some of the scale and cause spikes in your samples. So I don't think that it's the best idea to say, okay, these guys are out just because they've been compliant for a long time.
Great. Thanks, Brian. Just to mention, if you have a question for one of our speakers, put it into the question box on the dialogue box on your right, I believe. It pops up usually. Also, if you have more than one person in the room, if you haven't already in either the poll or prior, could you put down the number of people in your room so we can quantitate how many people we're reaching? So here's a question for Mike Schock. In reference to Marshfield, Wisconsin, what is the relationship between manganese and lead and copper concentration?
Okay, well, I'll answer that 2 ways. One of them is when you get the slides, we actually wrote a journal paper that included a discussion of that, and that reference is in the slide presentation. But just briefly to answer the question, what we found is that parts of the system that were fed with high manganese concentration wells created this manganese deposit. Lead from the lead service lines was then accumulated by several mechanisms onto that manganese, and so the protective lead-4 oxide scales that were present in other parts of the system didn't form in the manganese-rich areas, and so those places suffered prolonged release of particulate bound lead. And so that was basically the problem. So in areas where there wasn't manganese, they didn't have that problem.
Okay, here's a second question for you. Aeration can be effective for some water quality conditions. I'm curious why aeration has not been addressed as a treatment method.
I think the expectation was that it's encompassed under pH and alkalinity adjustment, because aeration really is basically both. And so it really is. I think it wasn't called out as a specific technology because it's got limited applicability. Certain water qualities it will work well, other water qualities it won't. But it's certainly intended to be an effective measure, and we know it can be a very effective treatment.
Okay, and another one for you, Mike. How would some of the discussed CCT and practices impact other metal releases, such as chromium or arsenic in water distribution systems?
Well, I guess there's several ways that would happen. One of them is would also be the question of changes in the background water chemistry. If those are existing long-term contamination sources, then anything changing the basic surface characteristics, oxidation reduction potential changes can certainly mobilize surface deposits, change the solubility of those metals. I think it's when those are on the pipe surfaces that needs to be part of the overall evaluation. Now, most places the compliance monitoring points are not out in the distribution system, but I think from a public health standpoint, it's certainly wise to look at what the treatment changes would do. In some cases, there may be further immobilization of some of the contaminants, but I do know of a couple, one system for sure, where they added a mixed phosphate chemical hoping to reduce the lead. levels, and they actually displaced the arsenic from the iron surfaces and got spikes of arsenic because the phosphate outcompeted the arsenic 5-oxyanion on the surface. So it's certainly something to keep in mind as part of it. It isn't necessarily a conflict.
Okay, great. Thanks, Mike. One note, it's 3 o'clock, so if you have to leave, thank you so much for attending the webinar, and hope to see you on August 18th for our next one on a DVP issue. If you can hang on a little bit, we have a number of more questions in the question box, and if you want to add in questions, feel free, and we'll go for however long, well, at least another 30 minutes if we need to, answering the questions as long as we can. So thanks so much for attending if you have to go. The next question goes to Brian D'Amico. Is the purpose of LCR monitoring to estimate the population's exposure to lead and copper, or to ascertain that treatment is necessary, or that the treatment system is working as designed?
As I discussed a little earlier, some of the sampling is going to be based on your higher risk areas. The largest reason for doing the sampling is to determine, when you have to actually implement your treatment techniques. It's not necessarily a means of estimating exposure on a nationwide basis. It's more about knowing where we have to do additional actions in order to keep lead and copper levels down in drinking water.
Thanks, Brian. The next question is, the LCR sample site selection requires that sample sites not be changed, but it seems that we now may not be sampling the correct sites. Is there a mechanism to require a system to update their lead and copper sample sites? You want to take that one, Mike?
That's more of a regulatory interpretation question. I think if a system doesn't have lead pipes, it's possible they can negotiate depending on what states want to do. It may be more appropriate to modify that. I don't know, Brian?
No, yeah, I think, like you said, it's more of a, I don't know if there's anything where where it can be required of a system. I think it's something more at the local level for implementation to deal with. I don't think that's something that we have necessarily, a hook at the federal level.
Okay, great. Thanks for tag teaming that one. This one is for Michael. How would some of the discussed CCP and practices impact? Oh, I've already covered that one. Do you have any information on the effect of the CSMR in regards to a coagulation change in treatment?
I don't think we have anything that goes beyond what's been published in the literature. I think it's pretty well established that there seems to be a relationship in some waters that if you do increase the chloride to sulfate mass ratio, for those of you that don't know what the acronym means, it's chloride to sulfate mass ratio. I think it certainly does play a role in some waters, but the mechanism really hasn't been worked out yet. So there are systems that seem to have a high ratio that have a problem, and some that seem to have the high ratio that don't seem to have a problem. It probably, I think the only thing that looking at the data that we see is the chloride concentration itself probably plays some role as well. But I think it's something certainly worth looking at if you're doing exploratory studies. If you've got a lead problem or a copper problem and you want to evaluate ways of treating for it, taking that into consideration while you're evaluating treatment options. I know a couple of consultants that are working with smaller systems that are looking at manipulating that ratio as part of the overall control process. So it's something to be taken seriously. It just isn't universally a yes-no kind of thing.
Okay, great. Here's a very specific question for you, Mike. If a water Langley or saturation index of -0.53, I believe I'm reading that right, what kind of treatment is recommended if the distribution system has copper in it?
Well, the Langler index is a calcium carbonate saturation index, and with copper chemistry, calcium carbonate coatings has never been shown to be the acting corrosion control mechanism. Copper is really a function of the pH and alkalinity of the water and some other, sometimes chloride or sulfate. So I think what I would do is look at the water quality analysis itself, the different parts of it, and look and see if this is. Chances are it's primarily a pH problem if it's a negative Langmuir index. Just because of the main parts of that index are the carbonate concentration, the calcium, and the pH. So I would say go back and look at what the pH and alkalinity of that water is, and whether or not they're adding phosphate or something else in the background that also could be a factor in inhibiting the passivation of the copper.
Okay, and here's another one for you, Mike. Where is the best location to add orthophosphate, after chlorination or before? And does it matter? Or does it matter?
I don't think it necessarily matters. Now, I do know some research has been done on one very large water system that tended to have too much alum carryover, and they actually have started adding the orthophosphate at rapid mix to precipitate out some of the excess alum so that it didn't go on out into the distribution system, and then they introduce phosphate again at a second point to trim the concentration. I don't think intrinsically it matters. There may be some specific operational engineering constraint at a given system that would dictate it better one place than another.
Okay, great. We have a couple more questions, I think, to ask. Again, if you have a few questions and you're still on the line, feel free to put them in the question box. This one is for Brian D'Amico. Can you ask your local water company to do lead and copper tests on local distribution systems such as a large apartment complex or a mobile park where water is supplied by them?
You can certainly ask. I don't know what there may be legalities with requesting sampling at something that's not, owned by yourself. As requesting, please come to my home and take a sample is different than saying, please go to, a location that is not mine and taking a sample. In either instance, I think you can request. If there's a concern regarding the lead and copper content, another option is you can go to your local box hardware store and actually purchase, do-it-yourself lead tests, and you can, I think you can either mail them in and get results, or sometimes they'll have a little simple color scale, and that's one way you can kind of get at least some, simple background information. But, certainly, the local water companies will, your PWSs will vary on their responses to whether or not they'll come out and do it, but certainly ask, yeah.
Okay, thanks, Brian. We have one more, I think, one more question, unless something else pops in. So this one's to Mike Schock. No lead service line in our system, all copper services. We have no exceedances of action levels, but we are pursuing a radium removal system for our sequestered high manganese groundwater, 0.099 ppm. Anything particular to be mindful of?
Yeah, I think this is a good case where probably if you're using some kind of media, it's possible that either the sequestrant or the manganese itself may also be a fouling problem, and it might be a good idea to get rid of that to try to design the system to not only, I'm not sure which media you have in mind with this, but it might be a good idea to seriously look at a manganese removal system as well as the single-use media for the radium in conjunction, and look at if the media, see if the media needs, what it requires for background water chemistry. I mean, some media tend to like lower pHs, and that would be a caution. But if it's something, depending on what your background DIC is, think about your new copper, whether the conditions are corrosive to new copper, and then see if the combination media and manganese removal would have any other adverse impacts on pH or alkalinity in the system.
Okay, here's one, Mike, that just came in. I have a very large municipal system with low copper levels, but also low dosage rates of orthophosphate and low levels in the distribution system. Should I be content with the low copper readings or be concerned with the orthophosphate readings?
Well, I guess I'm assuming from this question that it's not that the orthophosphate. Well, I'm not sure why it's there, whether it's there for lead from brass and solder or whatever. I would guess that. The question I would ask is, are the low copper readings in relatively new sites, or these are all 20-plus-year-old sites? And I would think about what is the background water chemistry and whether it's likely that the new sites would even have a copper problem. I mean, as I pointed out, even though small amounts of orthophosphate can retard the aging, if it's not an aggressive water to even new copper, it doesn't matter. You'll get higher copper levels, but it's not anywhere near any kind of a health threshold of concern. Copper, at least, the one thing about copper relative to lead is that the MCLG and the action level happen to be the same. So we do have a direct health-based standard with the copper. And so if you're substantially below that in new copper plumbing, I don't think there's really anything to be concerned about.
Okay, great. This one's for Brian D'Amico. Wouldn't a state-accredited water testing lab be better than those cheap home kits?
Yes, it would. The one thing the home kits do have, though, is they're readily available. You can get results relatively quickly. So in the event you're looking for a quicker answer, it's certainly something to go to, sort of a gross level screening analysis. But yes, the accredited lab would most likely be better.
Okay, thanks, Brian. There have been, this one's for Mike, there have been a number of references to alum carryover. Can you explain this more and touch base on if there is a problem with other aluminum-based coagulants such as PaCl?
Okay, there are two problems that we've observed with the alum carryover. And one of them is the fact that if you've got a system that's trying to add an orthophosphate or blended phosphate corrosion inhibitor, the phosphorus reacts with the aluminum, and so the phosphate does not make an effective lead or copper phosphate deposit on the surface of the pipe because you get this fouling because of this aluminum phosphorus kind of compound. One of the other things that can happen is hydraulically, sometimes these things have a huge adverse impact on C factors as well. And they deposit on the pipes. And so it's a bit of a double-edged sword because it can render the orthophosphate not good, not highly reactive in the way you intended, but it can put a diffusion barrier on the pipe. So the only way to find out whether it's good or bad is really, sampling sites, doing profile sampling and finding out if water contacting these deposits has high lead levels or not. So, those are the real impacts of the alum carryover. And actually, even if you're not doing phosphate addition, if you get too much aluminum in the distribution system, you can still occasionally get aluminum hydroxide precipitation, which is also another pipe surface fouling mechanism, which can then give particulate release of lead. So those are the main concerns with it, I think.
Okay, great. Thanks, Mike. A couple of people popped in and made comments that the state agencies can lead a person to a certified analytical lab. So that's something that our listeners have chimed in on. So here's a question for Mike. What tends to contribute more, brass versus brass or bronze fittings or valves?
That's a really good question. I think what it comes down to in the end, bronzes historically have had more lead content, higher lead content than brasses. But it really depends on the specific alloy, and it also depends on the shape of the internal parts of the device. So it's really hard. The tempting generalization is bronzes are probably worse than brasses, but it depends on whether they're cast or machined and what the surface area of that leaded alloy is within the device itself. So it's real hard to just universally say one rather than the other.
Okay, great. And I think I don't think we've answered this one, Mike. Does flaming a tap for Bactese samples contribute to lead and copper samples?
I have never heard anything about that one way or the other. I mean, inherently, I can't think of why it would, but
Right.
I can't say that I've ever had anyone study that.
Great, yeah. Okay, so I think in our question board, I think we've gotten anything. So I think we're left with, like I said before, if you've got an apartment complex, the state may have data for you, or they may direct you to an analytical lab that would be certified for lead and copper samples if you're interested. Other than that, I think we're all done with the questions that I can see. So thank you very much for attending, and thank you very much to our speakers, Brian D'Amico and Michael Schock. Again, our next talk or webinar is August 18th on DBP issues. And you can go to the web for a recording of this webinar if you wish, or recommend it to someone. Thank you so much for attending, and hope to see you next month. Thank you. Bye-bye.